Okay, so let's do a slight generalization of this. And the generalization is that now suppose that we have many different energy levels. Okay, suppose that we have, sorry. So say many different, say, energy levels. I is now an index. And let Ni be the occupation number of each level. So for fermions, it can be 0 and 1. For bosons, it can be anything. Then the Boltzmann factor for any given, the configuration is E beta N1 mu minus E1 E beta, say, N2 mu minus E2, dot, whatever, depending on how many energy levels we have. So we can express that as a product. This is a very, almost a trivial generalization of what we've been doing. Okay, so what is the grand partition function? So the grand partition function is going to be the sum over all the possible Ni's that are allowed by the symmetry times, well, with the summoned being this thing. Now the idea is that, Ni is actually independent of I. So Ni can be either 0 or 1 for fermions, or it's any positive integer for bosons. And because of that, because these two things are independent, we can exchange the order. And then inside, all we have is the same thing as before. And therefore, if I take the log of my grand partition function, this product then becomes a sum. And all we have is the same expression as before. But now with the sum over I. Okay, so this is our grand partition function. Now, okay. Now the thing is that, we can write like before, what is the expectation value? What is the average number of N? And that's given by 1 minus 1 over beta. Now partial, well, it was also partial before. And after a couple of lines of algebra, it's just going to be E beta EI minus mu plus minus 1. So we can identify this. So what is this? This is just the average number of particles for a given energy, right? So we can identify, the distribution function f of E. So f of E is the number of particles or let me see, Fe del E is the number of particles, with energy between, say, E and, E plus dE, then we can say F of E is, for fermions, it'll be beta E minus mu plus 1. And this expression is called the Fermi-Dirac distribution. And on the other hand, F of E for bosons is beta E minus mu minus 1. And this is known as the Bose-Einstein distribution. Okay. So I was teaching modern physics in the US many years ago, and I was teaching them quantum mechanics, the part of modern physics that is quantum mechanics, and I like to tell the story of behind every formula and how it was discovered. And so at some point, one of the students asked me, because most of the equations were discovered in Europe, right? So a student asked me at some point that, so was all of quantum mechanics discovered in Europe? My answer was yes, but a little bit of it was discovered in Bangladesh. And that has to do with the fact that Bose was in Dhaka University when he discovered the Bose-Einstein statistics. Okay. So any questions?
These formulas look very similar. Were they discovered independently? Because they have very different names.
Yes, they are very different. Their properties are very, very different. And at very high, like low, what should I say? When, let me see. So for example, for B, for beta mu, E minus mu much greater than, say, 1, they both reduce to what?
Infinity.
No, they both reduce to the Boltzmann distribution, right? So they both reduce to Boltzmann, or the Maxwell-Boltzmann distribution, sometimes it's called. Okay? And this means that, this limit corresponds to mu being small. That is the density, the density of the particles being small. Okay? So when the density of particles is small, even if we have fermions, it doesn't really matter because none of the fermionic states are doubly occupied. Okay, so what we'll do is that in the next class, we will look at application of one of these statistics. We shall look at the Bose-Einstein distribution and see how it is used to, how it was used by Einstein to predict what is now known as the Bose-Einstein condensation, which is kind of an exotic form of matter. And then if there's time, we might also discuss also a phenomena that is very, very specific to fermions, which is known as degeneracy pressure, which allows for neutron stars and the calculation of the degeneracy pressure allowed for Chandra-Shekhar to derive the limit, the mass of a star, the mass of a dying star that has to be over which it becomes a black hole. Okay, so both of these statistics have very, very important applications in astrophysics and condensed matter physics. So what I'll do is that I'm a bit early. Like I don't have more stuff in relationship to Bose-Einstein statistics today, but what I wanted to do is discuss a little bit about a consequence of the tensor product. Okay, so I wanted to discuss something which is known as entanglement.